Hello, welcome to another lecture on Introduction to Machine Learning. Today we will talk about a very important topic, which is linear regression. This topic is foundational for many of the advanced models that we will analyze in machine learning. However, advanced models, they are applicable to specific situations, and some even more advanced models keep getting invented every day. However, linear regression being a foundational topic is very important to understand because it gives us insights into how to analyze some of the more advanced models. So the objectives of this module are that the student should be able to write the objective for the regression function, and the student should be able to decompose the loss function of a regression equation into its bias and variance terms. We will talk about what is bias and variance, and also write the objective of the linear regression function. And then the student should be able to derive the analytical solution for linear regression and find what is the problem with the analytical solution and develop a computational solution which will lead to the same answer but which will be computationally efficient. Additionally, there will be advantages of using this computational solution, that we will be able to easily add regularization terms, and we will look at what is regularization also in this module. So linear regression sounds very simple, but we will also look at how linear regression is applicable in situations where we actually require a non-linear solution. So the outline will be as follows. We will start with the general regression problem, and we will look at its bias and variance decomposition. Then we will get into linear regression, problems with linear regression, analytical solution of linear regression, and then we will look at the computational solution of linear regression, and then we will develop ways to regularize the computational solution. Okay. So the general problem setting for linear regression is as follows. Okay. So let's say we have an input x, okay, and we will call it xi. Okay, so this is an input xi. Xi means it's the ith input, right? And with that we are given a target variable ti. Okay, so xi, I will write it as bold because it's a vector, and ti is a single value, it's a scalar. Okay, and this comes as a tuple, and there are several such values. So for example, we have x1 t1, x2 t2, okay, so and x is a vector, and up to, let's say, xn tn. So there are n such tuples for training. Okay, and what we want to do is we want to find a mapping from x to y, right? So we want a mapping from x to y, so that this y is close to t, as close to t as possible. So again, I will use the indices I. So we have the vector x, and we are going to estimate a scalar y, and this mapping will be based on some function f. Okay, so we have our xi, it belongs to d real numbers, it's a vector of d real numbers, whereas our ti and yi, they belong to a scalar, so it's just r to the power 1. Okay, so that's a general setting, and we want yi to emulate ti, so we want the function to come as close to ti as it can, and because of that it will reduce the error in the estimation. Okay, but we will see that there are other desirable properties of this function, and it should not always try to reduce the gap between yi and ti, and that is where understanding the bias variance decomposition will be important. That is where generalization in machine learning is important, because we don't want to be learning the mapping by rote and remember everything, every value of ti by rote by using a very complicated function. Okay, so first let us develop a loss function for this. So what is a loss function? Loss function is basically a function that we will minimize, and by minimization we will bring this yi close to ti. So what is yi? Yi is your estimate, and ti is your target value. and xi is input. Okay, so we will say that yi is equal to fxi. All right, and we want this to come close to the target as possible. So once it comes close to the target, it can go either above the target or below the target. We want to penalize both going above and below the target. So we will say that let us minimize yi minus ti, right? And we will take the square of that, and we will sum it over all values of I is equal to 1 to capital N. All right, and we might want to divide this by n so that it is an average value, right? And we might want to add a half in front of it. That is for analytical convenience, because we will be taking the derivative of this objective function. When we take the derivative, because we have the square, it will cancel out with the half. Okay. So this is going to be our loss function. So we will call it L. All right. And this loss function is something that we want to minimize. There are other choices for this loss function, such as we could have taken the absolute value of the difference between yi and ti as opposed to the square. However, we will see that this estimation, this driving down of the sum of squared or mean squared error, that has some nice analytical properties and interpretation, especially when we think that the residual, which is the error that is left, has a Gaussian distribution, and Gaussian distribution is quite a reasonable assumption in many practical situations. So this is called the mean square error, MSE. Okay, so this is the mean square error loss function, which you will see popping up quite often in machine learning.